Ladies and gentlemen, good afternoon. We are starting session on Power Systems 3. We have 4 papers in the session, and we'll be starting with the paper on transient response of the grounding grid. Could you please? You are Amaury Martins Brito, PhD student and a Master of Science in Electrical Engineering at this university. His main interests are low-frequency electromagnetic interferences, DC and AC electrical grounding and lighting protection systems. And he's been working since 2005 as a professional engineering, performing as the head of projects, services, and solutions directed to the industry. Okay, the floor is yours for 10 minutes. Amaury, thank you.
Good afternoon, everyone. My name is Amaury. I'm going to show you this work that is at the boundary between power systems analysis and electromagnetism. That is the transient response of a grounding grid subject to a lightning discharge. Well, I'll try to make this quick because, you know, after lunch, after the feijoada, I don't want you guys to fall asleep, okay? So I'll try to move to results as soon as possible. We're going to talk a little bit about lightning principles. I will describe to you the simulation model we built, and then finally, the results. Here is where we are. We have a transmission line, we have our phase conductors in blue, we have the shield wires in green, and finally the grounding conductors of the power line. We may have personal operating equipment, we may have pipeline facilities. So, the shield wires are intended to provide the protection cone over the power line to prevent damage, flashover, to protect people. Basically, what they do is to provide a safe path for a lightning discharge current to the ground. But this current, as the transmission line, it affects the environment on their surroundings. I mean, great magnitude current will flow through the tower, will be discharged into the soil by means of these grounding conductors, and so what happens? Let us first understand the lightning discharge model. It is basically a pulse of current, okay? In our model, we considered 30 kA with a rise time of 1 microsecond and a half-value time of 50 microseconds. So we get this shape here, which is basically a double exponential function, okay? Here we have a real case of a lightning discharge on a power line and the effect of the shield wires protecting the line in order to prevent line flashovers, system failure, and risk to human beings. So, this is our system we are to simulate. We have the tower made of steel. We have the shield wires also made of steel. We have the grounding conductors made of copper. And the steel foundations of the tower line, which is a frame, a metallic frame, surrounded with concrete. We consider the soil to be made of dry clay, so a high resistivity value. And then we simulated a lightning discharge over this structure. We used the FDTD method. I'm not going into the mathematics of the FDTD because it looks like black magic, you know. But basically, what it gives is a time domain solution to Maxwell's equations. We split the domain into very tiny blocks, and we compute the electric and the magnetic fields for every single cell that composes the domain. It is very suitable for transient analysis, and it provides means for modeling realistic installation structures. However, it comes at a cost. It has a heavy computational load. Okay, the simulation we worked here, it took 5 days to run, so it is a lot. But basically, here we have a zoom into our system and a discrete version of this tower. Look like that old video games, that old 8-bit video games where everything is squared and made of blocks and so. So let us look what happens when a lightning strikes over the tower. Let us look how the counterpoises, which are named the grounding conductors, and how the concrete foundations work on discharging this current to the ground. Basically, at the grounding conductors, you have, for that 30 kiloamps of the lightning discharge, we have a peak of 6.6 kAmps being discharged by the counterpoises, and which comes as a surprise, we have 2.1 Ka being discharged by the concrete foundations. So this is sort of unexpected because the concrete is a very poor conductor. So we see that the grounding resistance of the conductors go through a transient state, and then it stabilizes at 8 ohms. In the tower, we had a touch voltage, that is the voltage between the hand of a person positioned 1 meter apart from the tower, of 171 Ka, and the step voltage around the grounding conductors of 94 kV. So it is a lot of voltage. We can notice that the most active parts of the grounding conductor are the extremities, which agrees with previous results we had obtained using the method of moments for steady state analysis. We can also see the shielding effect that the shield wires and also the tower provides. You can see that we have a lot of energy around the shield wires, but they don't get to propagate to the region of the phase conductors. And you can see also that inside the tower, I mean, at the bottom of the tower, under it, there's no energy as well. There's no electric field. So we managed to see analytically something that we had from intuition. I mean, everyone knows the Faraday cage, but now we could see it using simulations. And, well, the FDTD provides a nice way to visualize the information over time. So I made an animation, and, well, let me cross my fingers and hope I don't embarrass myself. But here you can see it will loop through it again. Pretty much looks like a lightning strike. I mean, there is that flash over effect, and then the electric field vanishes over time. So it pretty much agrees with the physical behavior we expected. So what we concluded from this work is that the FDTD is effective to handle heterogeneities, multi-layered structures, concrete enclosures, I mean, really complex structures made of several different materials. What came as a surprise to us is that the tower foundations play an important role at discharging the lightning currents to the ground. We realized that in this case, for a typical lightning strike, the safe limits are exceeded, so there is the need for some mitigation actions. And finally, the shield effect we could see agrees with the physical behavior. I mean, you have just a Faraday cage. So that will be all. Thank you.
Repeating. Thanks, Amari, for the excellent presentation, and floor is open for questions. Professor Kleber.
Congratulations for your excellent presentation, Amari. And have you ever thought about it, a kind of, how can I say this, how can I use this kind of results to aid, for example, the utility guys to improve their transient analysis using EMTP softwares? Have you ever thought about it?
Well, most EMTP software use a circuit approach, right? We have been considering to use the ATP to generate fault waveforms and then inject this waveform into our FDTD program to see how this transient behavior goes through the shield wires and then the grounding conductor. So it is a plan to be executed.
Okay, very good. And another question. I have seen some works that put together in cost simulations two different kinds of tools. For example, dynamics analysis softwares with transient analysis softwares. And I don't know if it's possible to combine, for example, these kind of softwares with EMTP-based softwares. Have you ever seen something like that?
I didn't actually. I saw that once in a literature. There is a paper. They simulate the effect of a bank of capacitors on the power line, how the surges propagate, but they use a quite different approach. Okay, they use the method of moments to run the simulations on the frequency domain. They work with several frequencies. They make an interpolation to the spectre and then run a inverse Fourier transform to get the time domain response.
Any other question from the audience? Carrying on in the same lines as Professor Kleber. Regarding all the step voltage, you found very high step voltage there. How could you minimize? This will kill everybody on, I don't know, on what kind of a radius around the tower. So this cannot be if these are true results, you could not implement this
yes.
tower design. And how would you mitigate these results? And how would you get, regarding EMT simulations in these standards, ATP and PSCAD software, how would you get results? Because that's how they do it generally. How could you compare these results and justify the differences?
Okay, well, great question about the mitigation. There is a typical strategy that is widely employed in grounding system analysis, which is to cover the ground with an insulating material. So if you detect violation to the safety standards, you can use a layer like 10 centimeters thick of crushed rock, for example. It will not change the value of the step voltage itself, but it will create a higher allowable limit because it will isolate the operator.
Thank you.
Thank you.
We go now to the second presenter, which is Aloysio César dos Santos Jr., received his Master of Science at the University of Brasilia in 2018. And his degree was in 2008. So he's currently a PhD student at the University of Brasilia, and he worked previously in Infraero and Eletrobras furnace, and is presently dealing with money at the Caixa Bank. Not really, he's working on the energy sector there.
Thank you a lot, Professor Nelson. And good afternoon for everyone. This work was made by myself and Professor Damasceno and Professor Filomeno, Gama Faculty. And it's about an efficient start point to adaptive holomorphic embedding power flow methods. I will give some motivation to the work, a previous review about some existing power flow solvers, our methodology proposed, and experiments and results. So some questions for motivation of our work. You can get good results with the existing adaptive holomorphic embedding power flow methods, but is it possible to improve these techniques? Applying the Newton-Krylov and other strategies to initialize the main solver can provide good results. Some questions motivate our work, and will be more explained after. A previous review about the traditional power flow problem solvers. We have Newton-Raphson, Gauss-Seidel, and fast-decoupled load flow methods. But these techniques work well for operating points near system nominal conditions. If you have an elevation of, if the system is not in nominal conditions, these methods are passive to fail. Are dependent of a choice of initial voltage gas that could be near the final solution, and may diverge or convert to low voltage solutions, inappropriate solutions. And do not necessarily guarantee the non-existence of a power flow solution, a high voltage solution, in a divergence situation. To sobrepose these problems, Trias proposed in 2012 the method called holomorphic embedding load flow method, HELM. Is a new method, non-iterative but recursive technique. It's possible to find an operable solution if it exists. Então, is based on techniques of complex analysis, applies the holomorphic functions, which are functions infinitely differentiable around these radius of convergence. We apply, if a function is holomorphic, we can use an expansion of Taylor series of these equations. And after this, we apply an analytic continuation, for example, Padé approximations, to get the final solution. But the original Helm still have some problems. It converges slowly, implying an elevated runtime, demands high computational effort, and works on a flat start initialization. Are an inflexible method, which is a problem. In this, as a consequence, we have elevated runtime for getting the solution. Now about the existing adaptive Helm solvers. They are flexible against the original Helm. The adaptive Helm solvers are flexible, allow to use any system condition as initial guess, and not only a flat start, are able to consider the initial power injection in the system, and can use an initial estimate provided, for example, by Gauss-Seidel, Newton-Raphson, or fast decoupled load flow. These iterative methods are only an auxiliary method to initialize the main solver, which is adaptive Helm. So here we can see that the injected power are considered in this method, and CK corresponds to a voltage that can be for example, the voltage provided by the auxiliary method. Our proposed methodology. We identify in the literature that the adaptive Helm models existent use only the basic iterative methods as Gauss-Seidel, Newton-Raphson, fast decoupled load flow in a basic way. So we identify. So sorry, I have a problem. Oh, here. Then this work considers the use of some strategies to accelerate the convergence of the press solver. We call it our press solver as an assistant. And the press solver getting a preliminary solution until a defined tolerance error, for example, 10⁻⁶. And after this, the main solver with an adaptive Helm method, getting the final solution until the tolerance desirable. Our proposed efficient initializer uses BICG step, USB conjugated gradient stabilized based in Newton-Krylov method, for solving the system AX equal B. Precondition strategy, ILU factorization to minimize the zeros during the factorization. Approximate minimum degree MD, reordering to simplify the system. All of these techniques contributes to reduce the time of the press solver. So we have some results obtained until the final solution, which is 10 elevated to -8. We simulated 2-3 systems, but the most relevant is the 9241 business, which is a part of European system, and it is on math power. So we can see that the original Helm have the worst result, 28 seconds to getting the final solution. Newton-Raphson in a flat start demands 0.65 seconds and 6 iterations. When it uses the V0, which is a guess provided by math power, is near the flat start. Our assisted using the method proposed in this work, we have a reduction of time, 0.47 seconds. And the iterations is reduced a lot, 6 to 1. Our adaptive Helm In the basic way, which uses also the V0 provided by Matt Power, 0.46 seconds. When you use our proposed assistant, we have a reduced time, 0.44 seconds, which shows that our method is okay. Discussion. So the original Helm, due its inflexible starting point, demands an elevated runtime. Both Newton-Raphson and adaptive Helm present good results when using the proposed assistant. The assisted adaptive Helm obtained the best performance. For conclusion, this work presented an approach for accelerating the convergence runtime of a flexible holomorphic embed load flow method, adaptive Helm. And the results demonstrated that the technique proposed is more efficient than a pure initial guess, both for the traditional Newton-Raphson solver as the flexible Helm-based methods, resulting in an assisted adaptive Helm model. Thank you for your attention.
Thank you, Aloysio. The nice presentation. Do we have any questions from the floor? Professor Kleber.
Congratulations for your excellent presentation, Aloysio. Actually, it's only a curiosity about the Helm method. Actually, it's a very interesting method, but I don't know if you need to apply this kind of method, considering, for example, only the positive sequence network, or if you can use this kind of method in a free-phase power solution, power flow solution.
Free-phase. You are talking about the sequence of the...
Yes, because when you are working on a power flow solution, for example, for a transmission system, usually we consider the system balanced, completely unbalanced, so you can use just positive sequence network. But nowadays, with mainly due to the distributed generation (DG) in the distribution system, we are required to evaluate more power flow in distribution. But in distribution, you have so unbalanced networks. Yes. So it's not properly solved by using positive sequence solution. So you need to use a solution in a free-phase power flow.
Yes, now I understand your question. Thank you a lot, Professor Kleber. Yes, we have inclusive in the literature some paper that the author simulate a three-phase system with Helm, and he has had good results, but he don't consider the sequence, negative sequence, zero sequence in its study. But we can improve our paper, including this consideration.
Okay, what about the characteristics of XR relation of the system? Is there any kind of situation that it leads to the Helm solution to fail? For example, if you use a Newton-Raphson solution, depend on this relation, you can have a non-conversion.
Yes, one problem of this adaptive model is it passes to depend also as Newton-Raphson. Yes.
Okay, thank you.
The original Helm does not depend on any method, but he demands elevated time. So you have to choose the best solution.
Any more questions? Well, I have one question regarding controls. Power flow, you have plenty of discrete controls, taps and all that. How would this algorithm perform considering all this existing power flow controls and limits, Q limits and all that. This is when it turns, the algorithm may look real nice, perform better, but when you add all the other constraints, it may suffer or not. I don't know.
We consider in a static way. So we in our studies, we don't consider the type change, transformers, and variators, voltage variators, and we don't consider it yet. But we will consider in the future.
So let us hope
Yes.
it performs well. Thank you, Aloysio. Thank the audience for the questions. We continue to by calling the third presenter, which is Max Marques. Received his BS at the Federal University of the Rio Grande do Norte last year, and he's an MSc student at the same university now. And his interests are electrical machines, power system protection, renewable energy, and signal processing. I envy you with all these interests. Okay, you have 10 minutes.
Thank you, Professor Nelson. Good afternoon, audience. My name is Max, and today I will present the work entitled Assessment of Wavelet-Based Directional Overcurrent Protection in a Distribution System with the FIG. The authors are me and Monica Leal, and the advisors are the Professor Flávio and Luciano Costa. Barros, sorry. The wind-ended convention systems, known as VACs, is increasing. According to the Global Wind Statistics, in 2017, there are about 500 megawatts of cumulative wind capacity in the world. And the main VAX topologies applied in the wind parts are three: the PMCG, the Permanent Magnet Synchronous Generator, the SSIG, Skew Cage Induction Generator, and the Doubly Fed Induction Generator, where the FIG is the most applied today because some advantage. And when we relay regarding the relay-based protections, there are today some studies in the literature when apply the FIG in a distribution systems and analyze the behaviors of the relay-based protections. And these protections are responsible to protect the distribution system and ensure some grid codes. The grid codes are requirements imposed by the operators of the grid, and some of them is the low voltage right throw, which is the turbine need to remain connected in the electrical grid in case of a disturbance of the PCC, the point of common coupling, during a certain time. And to guarantee deliverability and protect the distribution system, today the most protections relay-based applied are the overcurrent protection and the undervoltage protection. However, these protections don't work properly to identify the direction of the power flow. So, some new studies are applying the directional overcurrent protection because this protection is able to identify if the fault occurs in the forward and in the backward. So, in this perspective, the goals of this work is to evaluate a new directional overcurrent protection in a 30-bus E3Z system, and in this distribution network is increasing the number of the FIGs, and it was implemented the Fourier-based directional protection as a conventional one as a comparison criteria. So, the directional overcurrent protection, the first equation represents the conventional one, and you have the torque equation, which is given by a voltage polarizing variable and a current operating current and the angle between these two variables. And the new improved traditional directional protection is based on the wavelet transform, specifically in the scaling coefficients, where it uses the scaling coefficient of the polarizing voltage and the scaling coefficient of the operating current. And in the table, you see the variables, the operating current and the polarizing voltage for the phase A, but there are for the other phase. When you speak about the DFIG implementations, we have some challenge when you insert this in the electrical grid, due to the presence of the power converters and the wide intermittence, which increase and decrease the state current. However, comparing the DFIG with another full power converters, only 30% of the generator active power can pass through the converters. I mean, only don't change severely the signature of the current when you use the DFIG comparing to another generator, one generators. But continue have the drawbacks of harmonic insertion, a reduction of fault current drawn from the substation, and occurs a power flow direction modification due to the different points of source locations. So, consequently, it's needed a fast detection to avoid miscoordination and undesired island operation. And in the table, you see some of the fixed parameters used to the simulations. And here is the system implemented, was it is a bus distribution system, which is divided in two parts. The first one is a distribution system with 33 kV and a subtransmission system with 132 kilovolts. And for backward faults was used the bars 24 and 25, and for forward faults was used the bars 22 and 24. And all the simulations was implemented in MATLAB Simulink in a frequency of 50 Hz. Was made 3 different examinations. The first one was the system without the figs and 2 different resistances. The first resistance was 1 ohm, and the second resistance was with 100 ohm to consider a high impedance resistance, a fault with a high impedance. You can see that in figure 2 that the phase torque to detect the directionality using Fourier and wavelet worked properly. And in the figure 3, the phase torque didn't work properly, but when you use the sequence components, the negative and 0 work properly too, for both. But it highlighted that the wavelet in blue acted faster than the Fourier-based protection. When you see the second case with 5 DFIG insertions on the electrical grid, you can see a similar behavior. But in figure 5, you can see in F that the Fourier-based has an oscillatory behavior, and the wavelet-based don't have this oscillatory behavior and has a better amplitude and faster than the Fourier-based protection. And in the last case, you can see that both protections act correct, similar to the others analysis. But in this case, and in some of the others, the overcurrent protections in figures 6 and 7 AB don't work properly. So an alternative to activate the directionality is used a wavelet transform as a trigger, the coefficient wavelet as a trigger, the stationary wavelet transform. We made some tests and worked properly for some cases. However, in another case, don't work properly using the stationary wavelet transform as an activator of the directionality. But it's probably that the stationary wavelet transform with boundary effect will work properly as an activator for all cases. So, it's evidence that the wavelet-based protection performed equal or better than Fourier-based protection through all evaluated cases, and the overcurrent used to activate the directional units is not reliable to all cases, But the current wavelet coefficient energy is a net alternative to activate the directional protection, and was tested also the stationary wavelet transform used, but is not enough to detect all cases. However, the stationary wavelet transform with boundary effect probably will achieve a better result as activator. Thank you.
Thanks for your presentation, Max. We open the floor for questions.
Congrats for the excellent presentation. It's a very, maybe a stupid question, but I would like to know what's the difference, since you are using the scaling factors taken from the wavelet transform, what is the difference by using your method and by using any other filter that we can take out all the high frequency components and keep analyzing the signal and time domain? It means that you analyze the signals in time domain and compare with other phasor-based techniques. It's really expected that time domain functions will operate faster, but if I use any other filter, what would be the difference between that filter and your wavelet-based method?
First, the wavelet has better performance and has a fast detection. If you use as activator a wavelet coefficients, energies, will instantaneously detect the fault and activate the directionality. So it's better than others. It's better than others to use the wavelet than the conventional ones. Was these questions?
It's just a comment, actually. Since you are using only the directional function, maybe you can use 32 protection function rather than 67, because 67 is the overcurrent directional. So in this work, it's only directional. So you have a 32 protection function instead.
You use both the overcurrent as activator, but
yes, actually in the 32 protection function you use a pickup, but it's a little bit different from the 67. It's just a comment.
Thank you.
A short question. Interlink with the tool protection commented by Professor Kleber, overcurrent and directional. How works the coordination of these protections?
First, the directional protection only trips if the activator with the overcurrent pass the pickup current. So after the pickup current, the overcurrent detects a fault, the directionality can work properly. But if you apply this first detection, that the directionality in the PCC, you can detect the fault in the instant of the fault and trigger the LVRT categories. There are three: the categories of hardware modification, control modification, and superconductor that needs instantaneous detection of the fault. But when we speak about the distribution system, the trip is given by the overcurrent, when the overcurrent pass the pickup.
Just a curiosity, what type of software you used in this
Software?
Sorry, I did not
MATLAB
read your
Simulink.
paper.
I used the MATLAB Simulink, the software.
You intend to use other software in future works, like ATP?
Until now, no, but I can think about.
Thank you, and I congratulate you for excellent presentation.
Thank you.
Thank you, Marx. Congratulations. Let's give a hand of applause. And we now call Mr. Yuri Ribeiro Damasceno. Hello, Yuri. Welcome. Received his BSc also from the Federal University of Rio Grande do Norte. He's an MSc candidate at the same university and develops research in industrial electronics and renewable energies. And also is interested in distributed generation, microgrids, and smart grids. Thank you. You have 10 minutes for your presentation.
Thank you. Good afternoon. I will present the paper, A Control Strategy with Seamless Mode Transition for a Low Voltage Distributed Generation System Without an Energy Storage System. It's quite a mouthful. So, what's the motivation of this paper? There's been an increasing demand for electrical energy in the world, and economical, technical, and environmental issues related to the conventional energy sources are hindering the use of these conventional energy sources. So, distribution generation, based on renewable energy sources are being connected to the low voltage grid. This implies a change in the grid to accommodate these renewable energy sources, and an alternative to integrate the renewable energy sources, the DG, is the microgrid. The microgrid concept is a small electrical system with distributed generation, energy storage systems, and flexible loads. And it's desired that the characteristics of this microgrid are that they can operate it autonomously and also connected to the grid. Why? Because if it is connected to the grid and something happens on the main grid, it can also function autonomously. So the transition between modes is a very important question because it can be harmful to the system if it's not done properly. So it must be smooth or seamless. It must not cause any transients, or better saying, it must not cause a lot of transients. This is a technical challenge because when the DG generation increases, the number of the DG generators increases, becomes harder and harder to ensure this. In the literature, there is several control strategies proposed. Some are based in communication systems, and some others don't use communication. The ones that use communication systems have a good performance, but they have this link that can be, this communication link that can be perturbed or broken, and this is a vulnerability. So this work proposes a communication-less strategy that provides a smooth transfer between modes and minimal controller changes. One distinguishing feature is that it does not require a storage system to maintain the energy balancing in autonomous mode. The system description is basically this. We have the DG with the renewable energy source and the inverter plus the DC link connected to the PCC through a LCL filter, and we have the grid, which is connected through a contactor, and we also have a linear load to emulate the loads of the system. One feature that I want to highlight is that the grid impedance is such that the R over X ratio is about 4, so it's neither predominantly inductive nor predominantly resistive. It's a characteristic of the low voltage distribution system. So the proposed control strategy has basically 3 modes of operation. The first, I would say that's the autonomous mode, where we have the VSI controller. We have the VSI controller that has all the current and voltage and power control inside. I don't show because of the time. And we have a PCC voltage controller that tries to maintain the PCC voltage at the nominal level, at the nominal value. And we also have an autonomous mode controller that controls the DC link voltage and also controls the angular frequency. Here we have an Icelandic detector that in this mode is working as it detects if the grid is present. When the grid appears again, it detects this and then sends a signal to start the synchronization. And the synchronization mode, we have another block that does the synchronization. They take values from the PCC and also the grid, and it alters the references and the reference for the PCC voltage controller and the autonomous mode controller in order to match the frequency and the phase and the amplitude. When the synchronization checker sees that the error is below a threshold, it commands the contactor to connect, and after a delay, it switches the controller. In the grid-connected mode, the autonomous controller is disabled, and the grid-connected mode controller controls the DC link voltage through the power reference of the VSI controller. And the detector, island detector, stays monitoring the grid for disturbance that have to that the grid have to, the DG microgrid have to disconnect. This is some simulation results for the grid disconnection and the grid connection. It's a little small, but it can be seen that the grid in orange, the voltage grid becomes zero. The grid voltage, sorry, becomes zero. Then the control switches here, and it's seen that the voltage or the power reference decays, and the power, reactive power reference also decays, and there is a little transient on the DC link voltage, but not very significant. It's 10 volts on 450 volts. When the grid connects, when the grid appears, there is a synchronization period. It cannot really be seen here, but I hope in the article we can see it. It starts the synchronization. The island detector detects this. It starts the synchronization. Then, after some time, it connects the grid. There's a little perturbation here. And then it changes the control. And when it changes the control, the maximum power point tracking algorithm takes over and increases the energy generated by the PV. So we have this little step in the current and also a perturbation in the DC link voltage. But when the grid connects, we can see that it doesn't perturbate very, very strongly. In this work, a communication-less control strategy for a PV-based RES DG was proposed. It is capable of operating in grid-connected as well in autonomous mode, and the energy balance in autonomous mode is maintained by controlling the energy, the power generated in the RES, the renewable energy sources. The strategy was validated through simulation, and it presents smooth transitions between modes and a relatively fast synchronization process. It's about 0.5 seconds. In future works, a more detailed model of the PV panel at the first stage of the DG will be used, and we aim to develop a suboptimal power point tracking mode algorithm to integrate in this control. Thank you.
Congratulations, Yuri. Nice presentation. So we now ask the audience here for comments.
I was expecting.
Thank you, Yuri, for sharing with us excellent results. Actually, this is a quite an exciting topic, and we have here at UNB very interesting in this topic. First, can you go back to your first slide? The first one, actually. So yes, when one are reading the title of your paper, maybe one can misunderstood and maybe can think that your scheme does not work properly if an energy storage system is connected. So can you explain a little bit about it?
About the title, or
actually, if your schemes work or not with energy storage system connected?
If yes. The energy store, it works in both cases. We chose to not use the storage system, because there is a lot of research already with storage systems integrated to the DG sources. So we use without, but the control developed can be used with a storage system with minor modifications, basically no modifications at all.
Okay, very good, very good. And another question actually is related to the possibility if you have more than one distributed generated connected into the system, and each one, in which one we are using this kind of solution. Is there any kind of a problem with this situation?
In this form, the bigger problem that we have is they can be a power imbalance, but this can be solved on using a droop control curve or other things. This is just the core that makes the system able to function. So there is this problem, but it can be solved quite easily, I think.
Okay, thank you, Yuri. And round of applause. Thank you.
Thank you.
We now go to the fifth and last presentation of this session. So we are calling again Max. He's been already introduced. He's an MSc student at the Rio Grande do Norte Federal University.
Good afternoon, I'm Max, and now I will explain about the work entitled The Performance of the Doubly Fed Induction Generator During a Voltage Sag. The main author of this article is Felipe Manuel Taveiros, and the advisors are the Luciano Barros and Flávia Costa. The wind energy conversion system, known as VAC, is increasing. According to the global wind statistics, in 2070, at about 52 megawatts was installed in the world. And the main topology used today is the FIG because some advantages. The one advantage is due to the power converter, which has only 30% of the generator power. But this topology, there are some drawbacks, and the most drawback, the worst drawback, is your stator winds, which are connected directly to the electrical grid. I mean, if a fault occurs at the electrical grid, the stator current will oscillate and generate electromagnetic torque pulsation. So, the grid operators imposed some code requirements, and some of them are the FRT, the fault height flow, or the low voltage right flow, which the turbine needs to remain connected on the electrical grid in case of a disturbance on the point of common coupling, the PCC. But when occurs a voltage dip on the PCC, the overcurrent increasing on the stator and the rotor winds, and occurred to a overvoltage on the power converter switches. So it's needed to know the behaviors of the FIG variables in this context of a voltage sag, which the variables, the flux, stator and rotor flux, the rotor and voltage, rotor currents and stators, and the voltage current, voltage in the stators and the rotor. And another variable that needs to be evaluated is the BENF, which is the back electromotive force that is induced by the faults that occurs on the stator winds. In this perspective, this works presents a theoretical and a simulation analysis of the defig during a voltage sag, and to support researchers in order to develop new control and protection methods to ensure the grid codes, and it was used real-time digital simulations in order to validate the signals. So, in this work is focused only in the back electromotive force, because this variable is responsible to cause impulse surges in the currents and the voltage in the rotor side, and can, in some events, cause the saturation of the power converters. So, in the first equations, you can, regarding by the rotor voltage equation and the flux equations, you obtain the first equations, which are divided in the two dynamics. The first one is referring to the rotor circuit dynamic, and on the other side, there is the Benz dynamic. And in steady state, in normal operation, the back electromotive force in your absolute value is given by the proportional value of the slip machine and the voltage stator voltage. But, when you refer to a transient operation, the back electromotive force are divided in three different parcels, and using the symmetrical component theories, and considering that almost all wind turbines are connected in a transformer with Y to delta, that isn't the zero component. So the last equation is referring the Benz referring to the state of flux synchronous reference frame, when the first parcel represents the operation in normal condition, where is the voltage amplitude by positive sequence and the slip machine, according to the last slide that I show you. And in case of a symmetrical fault, you have two parcels, the first one and the third one. And the third one parcels refers to the natural flux present in transients. And when occurs a symmetrical fault, we have the three parcels, the first one and the second one, which is referring to the negative sequence voltage. And you can see that in an asymmetrical fault, the Benz variable will behave according to twice the grid frequency. And in symmetrical faults, the Benz will behave according to one, the frequency of the grid. So they was implemented a system, a symmetrical and asymmetrical fault applied at the PCC, and no countermeasures were used, neither protection, neither counter strategy. The parameters are obtained based on the commercial available V90 versus conversion systems in order to reassemble, and was used the software LabVIEW, and the system is conditioned to a disturbance caused by an 8% voltage sag, which lasts 200 milliseconds. And in the table, it's specified some parameters used in the simulation. And before the fault operation, the slip was minus 0.12, and the Benz magnitude is near to this slipping, as I show you in before. So in a case of a symmetrical fault operation, you have the three-phase fault, and before the fault starting, in minus 0.1 to 0 times, you saw the Benz envelope is constant, but in the inception of time of fault, you can see the two behaviors, the increasing of the amplitude of Benz and the decayment time, a decayment, exponential decayment. So the Benz affect also the electromagnetic torque with pulsation. And when you see asymmetrical fault operation, another behavior occurs with the Benz. In steady state operation, in normal operation, is keeping constant, but when occurs a fault in the PCC, the bench has a bigger amplitude because according to the equations referred to the bench referring to the stator side, you have twice the voltage of negative component, and you have twice of the synchronous speed representing on the bench. For conclusion, the bench and the currents present high ripples after fault clearance. In both cases, the provoked damage conditions may last for several seconds after the fault clearance. The electromagnetic torque resulting in high ripples would represent a great mechanical stress, and which is one of the reasons why the machines got disconnected in events of voltage sag. And these scenarios occurred without countermeasures to evaluate the signals, and the aggravated Holter current flowing from the power converter could seriously damaging the power converters. For future works, it will be developed new counter strategies based on the bench signals and develop protection methods to act fast as possible to avoid the machine damage, and develop a fault identification using the bench because to each fault type, the bench has a different behavior. Thank you.
Thank you, Max. Congratulations. So we open the floor for your comments. Professor Kleber, you are very welcome. No doubt. Okay.
Please, you can go back, I think, 3 slides. No, the previous one. Yes, I'm so curious about the stator current, because as you can see, you have a large decaying DC component that maybe lead the current does not have a negative value in that way. So I'm so curious because I'm not sure if the magnetic performance, the magnetic characteristics of the stator is taken into account if you can reproduce some kind of a saturation phenomenon. Have you ever analyzed something like that, or your supervisor?
No, the saturation in the power converter wasn't analyzed.
Okay, thank you.
Okay. Any more questions? I don't know if I missed, but these simulation results are from what? PSCAD?
Was from the software lab view in real-time simulation.
And real-time simulation. So you have a...
No, was implemented by the first author, the Felipe Taveiros.
Okay. Thank you.
You are
Congratulations. And the session then is finished. Thank you all. And we go for the coffee break. Enjoy.